We are working on optimization problems, and in calculus class, optimization means that you are trying to find the best case scenario, where the best case scenario is either a maximum or a minimum. So basically, with an optimization problem, you find a formula that calculates what you're trying to optimize. You take the derivative, you find where the derivative is zero, and you should test whether that gives you a maximum or a minimum. In this case, we are trying to get to our neighborhood, and we would like to get there in the shortest amount of time. So we're trying to minimize time. That would be our optimum. Here I am 3 miles down the road from where the neighborhood is. I could go all along the sidewalk, so the longest distance, but on the sidewalk, I'm able to walk 15-minute miles. There's woods that are 1.5 miles wide that separate the sidewalk from the neighborhood. So if I went the shortest distance, I would have to walk all the way through the woods, and I can only walk 25-minute miles through the woods. It's possible that there might be some happy medium where I walk part way down the sidewalk and then I cut over through the woods to the neighborhood. So let's investigate that option. I'm going to let X represent the distance from the end of the sidewalk where I cut off into the woods. We already know that the woods is 1.5 miles wide. So if I cut across through the woods, the distance will be the hypotenuse of a right triangle, where X is one side and 1.5 is the other side. So the length of that will be the square root of X squared plus 1.5 squared using the Pythagorean theorem. If I've cut X off of the distance to the end of the sidewalk, then the amount I'm walking on the sidewalk is 3 minus X. It was 3 miles, I cut off X. Remember that rate equals distance over time, and therefore rate times time equals distance, and time is equal to distance over rate. So we're trying to minimize time. This is our formula that we want to work with. Part of the time, my distance is on the sidewalk. And so 3 minus X is my distance on the sidewalk. The rate is 1/15 miles per minute. Remember I said I could walk 15-minute miles on the sidewalk. That's a rate of 1/15 miles per minute. Then I add to that the amount of time through the woods. So the square root of X squared plus 1.5 squared is the distance through the woods. I can walk 25-minute miles through the woods, and so 1/25 is my rate in miles per minute. I'm going to clean that up a little bit. If I divide by 1/15, it's the same as multiplying by 15. So I'm going to multiply 3 minus X by 15. And dividing by 1/25 is the same as multiplying by 25. So I'm going to multiply the square root by 25. Now I'm ready with my time function to take the derivative. So dt dx, the rate of change of time with respect to x, will be 0 minus 15, because the derivative of negative 15x is negative 15. Over here, I have 25 times the square root of x squared plus 1.5 squared, but a square root is a 1/2 power. So I'm going to use the power rule. I'll multiply by 1/2. That was the original power. Remember, we always subtract 1 when we're doing the power rule. So 1/2 minus 1 will give me a negative 1/2 power. I leave the input alone. And then the chain rule says multiply by the derivative of the inside. So the derivative of x squared is 2x. And then the derivative of the constant is 0. So notice that the 2 and this 2 cancel out, and I can put the negative 1/2 power in the denominator as a positive 1/2 power in the denominator. And I'm now ready to set my derivative function equal to 0. So setting this equal to 0 and trying to solve for x, I'm going to add 15 to both sides. So I now have this variable expression set equal to 15. Next, I'll multiply by that denominator so that we eliminate the denominator. So by multiplying both sides by the square root, I get 25x equals 15 times the square root of x squared plus 1.5 squared. Now I'm going to square both sides. And so 25 squared gives me 625, and then x is being squared. 15 squared is 225. And when I square the square root, I get x squared plus 1.5 squared. Notice the square root gets canceled by the square. 625x squared is a like term to 225x squared. So if I subtract 225x squared from both sides, I get 400x squared. And 225 times 1.5 squared is equal to 506.25. I'm still trying to solve for x, so I want to divide by the 400. That gives me x squared is equal to 1.25625. That's x squared, so x will be the square root of that, and it turns out to be 1.125 miles. So what we found was if I started off down the sidewalk, but 1.125 miles from the end, I cut off and went directly through the woods, that looks like it'll be the shortest time. Let's actually find how much time that would take. So I'm going to plug this value for x back into my time function. Don't plug it into the derivative. You want to plug it back into the function that calculates time. So 3 minus 1.125 divided by 1/15 gives me 28.125 minutes down the sidewalk. And then when I plug the 1.125 in for x here, I get the square root of that number squared plus 1.5 squared. I'm dividing that by 1/25. That gives me 46.875 minutes through the woods. If I add those amounts together, it's a total of 75 minutes. So it'll take me a total of 75 minutes to go down the sidewalk and then cut across 1.125 miles from the end of the sidewalk through the woods to get to my neighborhood. We can test whether this is a minimum by the first derivative test, which means if I plug a number like 1, okay, 1 slightly less than 1.125, if I plug it into the derivative and I get a negative number, that means that I was heading down towards that value. And then if I plug a number slightly bigger than 1, like 1.5 in, if I get a positive number, it means that my graph was making a shape like this. So I was going down and then I started to go up, and so the minimum occurs where your derivative equals 0. And that happens here. That first we're decreasing and then we're increasing at 1.125 miles is where we hit the minimum. But in an application, it's possible that the shortest time, in this case we were looking for the shortest time, it might occur at one of the extremes. So we really should also test what the time is if I go all the way along the sidewalk, or if I actually go the shortest distance through the woods. It turns out it's going to take about 84 minutes to go all the way through the woods. But if I walk down the sidewalk and I walk the 3 miles and then I walk the extra 1.5 miles, it turns out that at my 15 minutes per mile pace, that only takes me 67.5 minutes. So this is an example where the minimum doesn't occur where the derivative is 0, but instead occurs at one of the extreme endpoints. So the extreme endpoint in this case is if x is 0 and I go all the way down the sidewalk the whole way, that'll only take 67.5 minutes. This scenario created a case where actually one of the endpoints was the better option. If we went all the way along the sidewalk and x was 0, that actually creates the shortest time. However, we could change one of the other factors and that might not be the case. What if we walked slightly faster through the woods? What if it took us 20 minutes per mile for a rate of 1/20th miles per minute? It would be interesting to recalculate this work and see if it's quicker to then cut through the woods at some point if my rate was 1/20th miles per minute. Why don't you do that as a challenge problem?